for 2 people to see. All right, so last time we had people talking amongst themselves and thinking about and talking about how they've sorted things before. And you have all sorted things before. Whether you like it or not, you have. You probably started when you were pretty young. You probably started sorting blocks. I don't know. But you've been sorting things. And if you've ever achieved your goal of sorting the collection of things you want to sort, well, you somehow systematically created a sorted collection. You executed some form of algorithm, whether you like it or not, you did. It wasn't code. But remember, last time we put that emphasis on separating the algorithm from the code. Sure, we use the code to express the algorithm, but the code is not the algorithm. The algorithm is the series of instructions someone follows. It goes back to the idea of the linear search. Start at the beginning. Is it the thing you're looking for? If it is, you're done. Otherwise, continue. That's the algorithm. The code of the algorithm is the thing with the for loop and the if statement. So these sorting algorithms, you've done them before. Like it or not, you have. And we had a couple of people talking about some of the ideas that they have used in the past. Some people have done things like what you were talking, like bucket sort, where you basically create a bucket for each letter of the alphabet, and now I can roughly alphabetize everyone's exam really easily. Just put, okay, you start with an A. I put you in the A bucket. D, you go in the D bucket, and so on. Sure, I've got all these little piles that aren't sorted, but good enough, whatever. Easy. It's sorted enough for me. But we had other people saying things like, well, first I go through and find like all the A's. And then I'll find all the B's. And that's close to what I would call like a selection sort. And then I had someone say like, well, every new thing you take, you add it to your sorted pile such that the sorted pile remains sorted. I think it was you. Was it you? Yeah, it was you. And there are other ideas. Did anyone spend time thinking about this and come up with one? Yeah.
I was thinking here, I always thought about just taking one and trying to separate everything based on where it aligns with one. So let's say I'm trying to organize a bunch of books. I take a book and it begins with the letter M. I put everything that has the letter before M on one side, everything else on the other side. So I can completely split it into like 2 different groups and just keep doing that.
Yeah, so that's how you sort books. You've done that.
Yeah.
No, you haven't. You're lying. You're just trying to show off.
That's basically how I've done it.
So, what else? Did anyone else think about how they've sorted things? There's one other really popular, obvious one that usually is the first one people think about. Yeah.
Can you sort things by their idea versus by the title?
By their what?
Like when I'm sorting my tablet on the computer, I sort them by subject.
Oh, yeah. Well, that's like your sorting strategy, but let's just say we're sorting numbers in ascending order.
Okay.
There. But we could define an ordering for anything we want, really. Like I used to sort all my CDs by like band alphabetically and then by year if there were multiple ones, right? Which makes sense. Although who owns CDs anymore? Any other ideas? So another really popular one is people will look at a pair of elements in the collection and they'll ask themselves, are they out of order? If they're not, leave them alone. But if they are, what should you do? Flip them. Just put them in order. So if you do that over and over and over and over and over again, you'll end up with a sorted thing. So to go back to what the discussion was yesterday, we separate the algorithm's idea from the code. They are separate ideas. So we will look at specific implementation, specific code that does some of the sorting algorithms, but those are just one possible implementation. The algorithm is the high-level idea. The specific implementation is the specific implementation of it. There are tiny little variations and maybe little differences you can do for each of them. But at the end of the day, there's still these like broad categories of like this is your insertion sort strategy, this is your selection sort strategy. And another thing that we were talking about yesterday was being really cognizant of how many steps are being done. And a lot of times we like to think of the number of steps being done in terms of n, where n is some arbitrary number that represents like the size of the collection being sorted in this case. Where yesterday it was the number of things in the list we had to search. My goodness. Was that the same person twice or two people once? Same person twice, okay. So, we'll start with this one here, insertion sort. This is basically what you described. And I'm just going to explain the idea. Here is the idea behind insertion sort. You start with your list of unsorted things. Okay? Then you start with an empty list that's called my sorted list. Now here's a funny question. Is an empty list sorted? Is there anything out of order in a list that has nothing in it? No. No. It's kind of weird, right? How about a list with one thing in it?
Yes, it's sorted.
It's sorted. It's kind of funny, an observation, but interesting to note nonetheless. So, I've got this unsorted list and this sorted list. That starts empty. But for each element of the unsorted list, I'm going to take it and put it in the sorted list in the proper spot such that the list remains sorted. That's what we have here. For each element, I insert the element into sorted list in the correct spot. For example, if I'm asking to insert 5 into the sorted list 137, I should end up with 1357. Okay? So the first sorting algorithm I want us to take a time to visualize is going to be insertion sort. And here's some code implementing insertion sort. Again, this is just an implementation. What do we see? Well, insertion sort in list, and we start with an empty list called sorted list. For element and in list, so for each thing in list, start a counter I. Well, I is less than the length of the sorted list, and the current element is bigger than what? The current thing we're looking at in the sorted list. So basically, this while has two conditions in it. The first one is while there's still things left. We don't go off the edge of the list. But the second big thing here is while the thing I want to insert is still bigger than the thing I'm looking at. Because if it's bigger than the thing I'm looking at, it must go after it. I should increment I. And that's what happens. If it is bigger and there's still room left, increment I. If we ever get to a spot, so let's say if we look at this example, 137, I've got 5. Okay, I is 0. Is 0 less than 3? Yeah. Is 5 greater than 1? Yeah, all right, increment it. So now I is 1. All right, it's still in the list. And is 5 greater than 7? Yeah. Is 5 greater? No. 5 greater than 3? Yes. Is 5 greater than 7? No. So I get here and I say, well, 5 is not greater than 7. Where should I put the 5? Not a trick question. Right after the 3. Basically, I'm looking at the 7. I had just 1 moment ago concluded that 5 is bigger than 3, right? And that's why I went to the next number. So I must have concluded that the thing I want to insert, the 5, is bigger than the thing at the previous index, the 3. So it must come after that 3. But we just saw that, well, 5 is not bigger than 7, meaning it must go where relative to 7? This is not a trick question. Before 7. So it must come after the 3, but before the 7. I think we found where it belongs. We put it there. And we just do this process over and over and over and over and over again. So who wants to get sorted with insertion sort? By height. Oh, a moment ago everyone's hand was up. All right, come on down if you want to. I want to have at least 8 people. 1, 2, 3, 4, 5, 6. Wow, okay, this is great. This might take a while, but it's okay. Here's how we're going to start. We are going to have, actually, everyone who's come down, I'm going to have you all just stand down there. This is the unsorted list. Sure, I know it's a list, and you're going to say, yeah, but they're not in like a linear, it doesn't matter. They're just this like bag of unsorted things that I want to get sorted. And what I'm going to start to do is have everybody get put it in the sorted list, starting here, and it'll go that way until we run out of room, or everyone's sorted. And we're going to sort based on height. Shortest person here, tallest person there. And we'll do our best. If people are really close in height, we'll see what we can do. All right? So I'm going to arbitrarily select one of them, because it really doesn't matter what order I pull from the unsorted collection. So someone step up. Okay. All right, where does he go in the sorted list? Wherever, at the beginning. Go stand right over there. Notice that this list is sorted. All right, someone else come. Now, while doing this, I want you all, including props, to think about how many steps are being done. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 individuals here. So I want us to think about how many steps are being executed here relative to 12. I'm not looking for a hard number. I just want you to kind of think about this and maybe generalize the 12 to n. And think about a best case, worst case as well, whatever that means. And if anything I just said is leaving you scratching your head, don't worry, we're going to talk about it. Okay, we need someone else to come on up. All right, so let's have you stand right here for a moment.
Oh, no.
And the question we now have is, okay, well, where on earth does he go into that sorted list? So if we follow the code that I have there, but again, we don't need to follow the code, it's the algorithm. We're effectively going to do a linear search through our sorted list to find where he belongs. Right? That's basically what it is. So let's start at the beginning. Let's compare the two of you. Okay, where should he go relative to him? Before. Awesome. Done. All right, someone else come on up. All right, we'll have to do another linear search to see where he goes. Well, no, you're skipping steps. Remember, we're stupid computer scientists. We have to do every step. All right, is he bigger than him? All right. Step aside. Is he bigger than him? Looks, yeah, it's hard to say.
Yes.
I think he's.
I don't know. Go back to back. This one's tough.
He's
Yeah, I think he's got you by like a centimeter. All right, so you go here. Great. Another one. Someone else just come on up. All right? And we'll start here. Is he bigger? Yeah. All right, so you must go, okay, is he bigger than him? No. I don't think so. All right, great. Someone else come on up. And we'll have you go.
down.
You're going to stand next to every person as you go to find where you go. So smaller. Keep coming. Smaller. Keep coming. Wait, smaller.
Yeah, what are you doing?
I don't know. Where am I? What time is it? All right, someone else come on up. All right, start at the beginning. Okay, you're bigger. All right, come on down. I don't know.
I think it goes to him.
Yeah. Think it goes to him?
I'm
All
so
right, there we go. Someone else come on up. All right, start at the beginning. Does he go there? No. Keep coming. No. Keep coming. No. Keep coming. No. Take your hat off.
Ooh.
I think you go between the two. What do we say? Does that
Yeah.
seem right? Yeah. All right, someone else. Okay, you're bigger, you're bigger, and you stand up straight. I think, take your hat off.
Okay.
I think she's, ooh, that's tough. What do you say?
Like this much of a finger shorter she is.
She is? Okay, all right, so go between them two. It was close though. This is where sorting people by height can get tricky. We should have just done it by name. Or age, yeah. But everyone's going to be like the same age. All right, someone else.
Ooh.
All right, I think you're taller. You're taller.
Oh,
shorter, I
You
think.
think shorter? All right. Go in
I'm just
between
so
the two.
tall.
There we go. We are
I'm really proud of
inserting
you.
her in the
Me
proper
I
sorted
guess I'm on
location.
YouTube right now.
We got 3 more. Come on up. All right. Okay,
Dang
bigger, 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 bigger. Ooh, now it's getting tough. I think. Ooh. Go back to back. This is really tough.
Oh.
Oh, the hair is confusing.
I can't see from down here.
We're just gonna pretend that you were a hair shorter, even though honestly I couldn't really. I wouldn't bet money on that. All right, someone else.
Second place for them.
All right.
What?
Okay, taller, taller, taller.
What did you come
Keep
behind
going
us?
until you find where to go.
Probably here.
No, keep going.
Oh, keep going, keep going.
Yeah, go a little bit. I think there. That's good. Yeah. And last but not least, of course.
Hey,
Go, Haley.
All right, keep walking.
Oh yeah. One
Does
more.
she keep going?
Yeah. Yup.
Is that right, or does she have to keep going?
What? Like,
Oh, I think.
I don't know. I'm assuming your hair's up. So.
I think you're in between. I think, right?
There we go. Let's pretend this is sorted. Wow, wonderful. Hey. So, we've obviously sorted people now. They're sorted. We executed an algorithm. We did insertion sort. We took everybody from the unsorted collection and put them into a sorted collection, and every time we added something, we inserted it in its proper spot, such that the sorted list remains sorted. That's what we did. Raise your hand if you think you've ever maybe inadvertently used this algorithm before without ever thinking about it. I know I have. Of course. It works. But again, computer scientists are weird. We do something one day and realize, can we formalize this? Can we get geeky and think about how much work was being done with these arbitrary tasks? But sorting is a big one. Now, go sit back down for a couple minutes and maybe we'll bring you back. Let's thank the prof, of course. So, with this insertion sort, how much work was being done in total? Did anyone get a sense of how much effort was required for that sort relative to the number of people in the sort? Can you please explain what you mean?
Every time you add a person, you have to go through about half of the people you already went through. So about n squared divided by 2.
But why n squared though? Can you keep going?
Let's say I've added 11 people, and now I have to add the tallest person because they happen to be last. I have to go through every single person until I get to the end.
So you're describing the linear search part really well. So you've got the n for the linear search, but why is it n squared?
Because you have to go through that many people every time you go through it.
There we go. We have n individuals. And the worst case scenario is, let's say I, by freak accident, always pull out the next smallest, shortest person. So we start with the shortest person. Then we take out the next shortest person, then the next shortest person. We inadvertently pull these individuals out in that order. Every single time I do that, I have to go all the way down that list. Right? I start with one person, then the next tallest person, well, they don't go in front of me, they have to go. So every time, I need to compare to everybody in that list, in the sorted list. So we have n people, and we effectively have to do a linear search for each of them. So if we are doing n linear searches, well, that's n times n work, n squared. Now you might be thinking, well, hold on, because you were saying, on average you're going to be like halfway, and the first time through you only need to, you don't compare to anybody. Then the next time you only compare to one person, not n. As you add more people, sure, you have to compare to more and more people, but at the beginning, you're not really comparing that many. Sure, at the end, you're doing maybe n, your linear search has to go through all n, but at the very beginning, you're only going to be doing a small number of comparisons. Right? Does that make sense at least what I just said? Because the first person I put in the list, how many comparisons did I have to do? Zero. Then I negated the next person. I only had to do one comparison. Then let's say the last person happens to be the tallest. I have to do n comparisons. Or I guess n minus 1, right? Because that's the person being added. So it feels like, okay, well, yeah, worst case scenario n squared, but it feels like it's not really, though, because it feels like we're only, like the first time through, we're only doing 0, and then 1, and then 2, and then 3. Does anyone recognize this sequence? The first comparison we do 1, or 0, then 1, and then 2, and then 3, and then 4, and then 5.
Could be like a factorial.
A factorial? No, but your brain's in the right spot. You're thinking the right way. You're just using the wrong operator. Because let's say I want to sum up all of those things. Well, the first time I do 0 work, then 1 work, then 2 work, then 3 work, then 4 work, and I want to add it all up. Just 1 second. I'm just... Perfect. Where the hell? Does it not have an opening?
Oh, it is.
There it is. There is no opening. Oh, okay. This is the hardest thing I've had to do today. So we can kind of think about the total amount of work being done. No, don't need to look at all the work I'm working on. What the heck? There we go. The first time, look, I have n individuals. I have 12 people, but let's say n. We start at 0, then we went to 1, then 2, then 3, all the way to like n minus 2, n minus 1. At the back, can you see that at all or whatever? Okay, cool. So the first time I do how many comparisons? You know what? The first time I do 0 comparisons, then I add that 1th person. Remember, we're computer scientists, we start counting at 0. I add that 1th person, so I have to do 1 amount of work. Then 2, I might have to do 2. Then 3, gotta do 3. And then I'd have 4, all the way down to n of them, n minus 1 of them, I guess. Right? So it's like we're filling up this thing. Do we kind of see that? So it is a summation. So what do we call, so if the first time through the loop, I'm doing 0 work, the next time 1 work, 2 work. For easy math, we're going to forget the 0 and start counting at 1 and go to n. 1 plus 2 plus n minus 1 plus n. Right? That 6 is not helpful. Right? What does that look familiar to you? What do we call that? Who here has graduated grade 10 math?
Is it Fibonacci?
No. No, but again, your heads are in the right space. You're just thinking way too hard. Who knows what we call this? Raise your hand if you finished grade 10 math. So you should feel terrible about yourself for not remembering this, because math is the most important thing. What do we call this? Someone yell it out. A running total. Do you have another word for that? Because you are absolutely correct. Addition. What are you saying? What kind of series? Wait, someone said it. A simple series? Well, yeah. But it is a series. A blank series. I'll give you a big hint. Additive. Oh my gosh, you guys are terrible. Arithmetic series. That's what you call it. Now who goes like, oh yeah, I remember, yeah. Well, Right, like who here remembers in grade 10 also learning like, hey, if I ever have this arithmetic series and I want to sum up the total number of things, like if I want the answer to that, do I have an easy way to calculate it like that without having to go through and adding them all up one by one? You had a question or comment? No? Okay. N plus 1 multiplied by half of n. Who here remembers something at least similar to that? Couple people? Okay. So, who here at least remembers hearing the story about, and I can never remember who it was. Was it like Euler or Gauss? Or who was it where they were apparently like a little shit in math class? And so their teacher's like, all right, go add up all the numbers from 1 to 100 just to give them busy work. And then they came back. I don't know how true the story is, but it's always the story that everyone says. And then he comes back in like 2 minutes with the answer, and the teacher's like, well, how the hell did you do that so fast? He's like, oh, it's easy. All you have to do is like this. What are they teaching you these days? You remember it? One person? Okay, so I'm willing to bet you've all had, don't go back and tell your math teachers this, but I'm willing to bet that you all had really bad math teachers. What? And here's why. Here's why I'm going to say that. And here's why computer scientists are often overly mean and critical towards mathematicians. Because the computer scientists are so obsessed with how we get somewhere instead of getting somewhere. Right? We care about the algorithm. When I give you an assignment about making tic-tac-toe, do you think I give a shit about tic-tac-toe? No. Maybe I do. No, what I care about is getting there. What I want you to do, I don't care if you get the answer. I care that you get to the answer. It's the journey, not the destination. Right? But it is. I'm not being silly. It is. So the computer scientists are always so obsessed with the how. The methodology, the strategy, the algorithm, if you will, of how we get somewhere. And a lot of time the mathematicians, they'll prove it once and then just remember and then they're good. Right? So as someone who's obsessed with the how, I get mad when the how is not taught to students in grade 10. So you remembered something like n times n plus 1, you said? And
n plus 1 times
n divided by 2. Yeah. So, the fancy formula, you put it in. If you want to know what the sum of all these numbers are, the sum of all the numbers from 1 to 100 is 100 times 101 divided by 2. It will be. That's the answer. But of course, you're left going, but why the hell does n times n plus 1 divided by 2 work? Right? I gave you the secret magic formula. You plug it in, you get the answer. But you, as good computer scientists, should be going, but why? How do you get that? Why is that the case? Does anyone remember, the why, the intuitive why to this?
If you look at each of the numbers, the first and the last number sum to n plus 1.
Exactly. So we'll stop you there, and we're just going to show this right on this side because it's clear. So if I have 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. Right? And there's a plus here. So all the numbers between 1 and n, I want to add them up. But if n's a million, that's going to take a while, right? If n is a million, I need to go, okay, 1, 2. If n's a million, and I'm literally looping through this to add them all up, create a running total, how many steps is that going to take me? A million, right? It kind of sucks. Where if you know that magic formula, it takes you 1 step. Sure, like 3, but good enough, it's 1. It doesn't change as n gets bigger. It takes the same amount of time. It's constant time. So here's the trick. Here's the intuition behind that magic formula that you may have had to memorize at one point in your life. It's exactly what you were saying. Here's what we're going to do. We're going to double this sequence. We're going to multiply it by 2. But we're going to remember that we multiplied it by 2, and then later we'll divide it by 2. Okay? Deal? So we're going to double this sequence. So I have, again, 1 plus 2 plus, and so on. But I'm going to do one little thing. I don't like writing it this way. I want to write it this way. 1 plus 2 plus 3 plus, and then this would be n plus n minus 1 plus n minus 2. Pretend that's on the same line. Does anyone notice anything interesting here? What is the sum of, let's say, with addition, it doesn't matter the order that I add things in. 1 plus 3 plus 5 is the same as 1 plus 5 plus 3, which is the same as 5 plus 1 plus 3, and so on and so on. The order doesn't matter. So here's what I'm going to do. I'm going to simplify this a little bit. I'm going to add this number and this number together. What is n plus 1? Who's? There we go. Did you say 1?
I said 1, yeah, I meant to say n plus 1, sorry.
All right. I'll go down here. So n plus 1 is n plus 1. What is n minus 1 plus 2? This should be the easy part. What is n minus 1 plus 2?
N plus 1.
N plus 1. What is n minus 2 plus 3?
N plus 1.
I greatly appreciate that vigor. You know, n plus 1 plus ... And then if I get here, what is n plus 1? N plus 1. Great. I've done that. So I doubled my sequence. But then I added these two together, then these two together, then these two together. So the total number of things I had originally was n. Then I had 2n, but then I added each pair together. So how many n plus 1s do I have? Everybody yell n. Oh. So the total sum would be n plus 1 plus n plus 1 plus n plus 1 plus n plus n times, which is of course the same thing as n plus 1 times n. But what did we do originally that we have to undo?
Multiplied it by 2.
We multiplied it by 2. So we have n times n plus 1 divided by 2 because we doubled it originally. We want to get rid of the other half. If we go back to that square example, geometrically, what I was trying to draw here, it's kind of like, here, I'm going to draw it again, but as a square. And this is n, and this is n, okay? There's n things total. We start at 0. We go to, or let's start at 1. We go to n. We start at 1. We go to n. So we have this n by n square. The first time, we didn't have to do any comparisons. Then we had to do 1 comparison, 2 comparisons, 3, 4, 5. All the way to the end, we had to do n minus 1. We effectively started by doing 1 thing, then 2 things, then 3 things, 4 things. We end up with this triangle, or half a square, which is interesting because we have n times n plus 1 divided by 2. Well, n times n plus 1, well, that's close enough to n times n. So we've got this literal square here, But we only have half of it because, well, the first time we had to do 0 comparisons and 1 comparisons and 2 comparisons. And then at the end we had to do a lot more. So we literally have half this square. Which, if I'm looking at n times n plus 1 plus or divided by 2, like if I wrote 1/2 times, I'm going to just multiply out n plus n times n plus 1, which is going to be n squared plus n, right? If you remember grade 9 math. Right? So we have that. Now, from what we saw yesterday, you might remember coefficients we don't really care about. Because sure, they definitely do affect the total amount of work, but we got to remember, one, we're really more interested with how it grows, what it grows like, how the amount of work being done grows as n gets bigger. And n versus half of n, well, they're still growing basically linearly, right? And if you're not comfortable with that, really the second big idea here is, well, it's a hell of a lot better than n squared. And we saw that n squared example. So we're really interested in with these like big differences. We'll say it like asymptotically follows this curve. So the 1/2 we don't really care about because it's just a coefficient. It doesn't really affect the growth, you know? So we don't care about the half. And then we saw n squared plus n. Okay, we saw the difference between n squared and n. When n was 1,000,000, anything that was linear took 1,000,000 steps. When n was 1,000,000, anything n squared was 1,000,000 millions. What's bigger, 1,000,000 or 1,000,000 millions?
1,000,000 million.
Obviously, how much bigger is n squared compared to n when n is 1,000,000? N times or 1,000,000 times. What if we made n 1,000,000,000? Well, now it would be 1,000,000,000 times. Basically, the amount that n squared takes up, the total amount of this expression, is so big relative to this, as n grows, we don't care about this. We don't care. In this particular example, with insertion sort, I would say it's an n squared algorithm. We saw linear algorithms like linear search. We saw a logarithmic algorithm, the binary search. This is a quadratic, n squared. As n grows, the total amount of work you have to do grows like n squared. Where with linear search, as n grows, the total amount of work you have to do grows like n. But because we've got this funny relationship, we have to do like this, like n things for each of the n things, we've got this like n squared scenario. And that's a lot of work. If you had an algorithm to solve the same problem, I'm not talking about sorting. If you had an algorithm to solve the same problem, one algorithm can run in linear time, n, and one could run in n squared time. Which one's better? N. The linear one, because it's way faster. It's going to require way less computing. Saves energy, saves time. That's good. It's these ideas where we as computer scientists would say something like, your algorithm is better than their algorithm. Because at this stage, how many of you have been like writing, you got your assignments done and then you kind of want to show off to your buddy like, oh, I did this really clever. Right? And you're like, my algorithm's better than yours. Well, okay, cool. But as far as a computer scientist is concerned, it's this type of stuff that we would use to discuss what's better than something else. Now, in the heavy duty, very narrow areas, sorry, not narrow. In the heavy duty areas where you start to focus on very specific problems and trying to optimize an algorithm to solve a problem, you might start getting down to very nitty-gritty details where it's very granular. But at our stage, we're going to think of things like linear, logarithmic, n squared. There's also like n log n. So it's not n times n, it's n times log n, which is better than n squared, but worse than n. We care about this pretty I don't know, what's the word I'm looking for here? Pretty low resolution of different growth functions. We don't care about a lot. Sure, there are some that are like n times log n, but no, those are very special cases. We really, at this stage, are going to care about things about like, well, my algorithm, this algorithm to do this runs in constant time, linear time, logarithmic time, quadratic time. Those are the things we care about. But there are problems out there where we're dealing with n factorial. So if you think n squared is bad, n factorial is crazy. Because n times n is going to be a lot less than n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n, and so on. So if you have something that's like factorial, ooh, you're in trouble. Though sometimes that's kind of what we're stuck with. So that's insertion sort. And this is kind of how we think about this as computer scientists in terms of like, well, how much work is being done? But of course, yesterday we talked about other sorts. We talked about selection sort. Is selection sort better or worse, or basically the same? Because it's funny. Going back to the beginning, when we started doing insertion sort, I told you to think about the best and worst case scenario. The worst case scenario is if I end up taking out the smallest, shortest remaining person from the unsorted collection and added them to the sorted collection. Because if I always end up taking the next shortest person out, I will always need to compare them to everybody in the sorted list because they're bigger than all of them. So I'm going to go, are you bigger, are you bigger, are you bigger, are you bigger, until I get to the end when no one's bigger. So the worst case scenario is I've got to go through the whole sorted list every single time I want to insert something. And any idea what the best case scenario would be? Like what the configuration of the unsorted collection would be to get me a better option? I think you both said the exact same thing. You start by picking the tallest person every time. Now, of course, if you're thinking, well, why wouldn't you then write your code to always pick the biggest thing? Well, you're sorted. You don't know what's what. You're getting this stream of things. We just get this, by chance, we end up with the tallest person remaining. We put the tallest person there, and then I take out the next tallest person. If this happens, I'll only ever need to compare to one person. I will go, are you bigger? No, okay, you go in front. The next person, are you bigger? No, oh, you go in front. I'll never have to do a linear search. I always just compare to the first thing. So the worst case scenario is this n squared situation, but the best case scenario is actually only n. We can get really lucky and end up with a linear time version of this algorithm. Now the algorithm is quadratic, don't get me wrong, but it just so happens that in this very special case, we get a much better runtime. So the runtime of this also kind of depends on the configuration of the data, which is neat as well. If we talk about other sorts, which we will, I guess, on Friday now, and we'll continue sorting students. Did I ever talk about the traveling salesman problem to this class? No. Okay. So there is this problem. I'm a salesperson. I live in Halifax. And I want to visit 25 towns/cities in Nova Scotia. And, I'm not going to go from, let's say I've got to go from Halifax, I want to go to Truro, Yarmouth, and Cape Breton, I want to go up to Sydney, whatever, right? I've got all these cities to visit. What I'm going to do is I'm going to leave my house in the morning, and I'm going to return to my house at night. And I want to visit all of these cities once and only once, except for the one I'm starting and ending in. So I'm going to start in Halifax, visit all the cities, and end in Halifax. But I want to minimize the total distance traveled. Meaning, it would be really silly for me to start in Halifax, go to Sydney, go to Yarmouth, go to Port Hawkesbury, go to, what the hell's the name of it? Wolfville, you know? I'd be backtracking far too often. So I want to visit all these cities as fast as possible. Like in the shortest total distance traveled. Do we understand the problem? It's a fairly straightforward problem. I've got a map, I've got all these cities. We got to visit each of these cities such that the total distance traveled is minimized. So, city, 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 city. And we'll assume there's a road you can get from any city to any other city. So, if I'm starting here, whoop, that wasn't supposed to happen, but that's okay. How would I go visit these cities? It would be silly for me to go like from here to 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 there and then back home. Like that's ridiculous. That's a bad path. Now you as a human, you go, well, I mean, that's obviously crap. I'm just, I would probably just figure this out. But the problem is there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I think, cities. I may have miscounted, but let's say there's 14 cities. The problem is what happens if there's 100 cities? So you know what, though? There is a very, very simple algorithm. Any of you could write. Very simple algorithm that will guarantee that you find the optimal route. It's very easy. All you have to do is try every single possible permutation, calculate what the total distance is, and then once you've done that for all permutations, just find and pick the one that's the shortest. Would you agree that that algorithm would totally work?
Yeah.
Great, yeah, of course. It's a simple problem with a simple solution, but we got a problem. How many possible pathways are there for 14 cities?
14 factorial.
If the first city, let's say the first city is fixed. I have to start in Halifax. So there's n cities, I have to start in Halifax. How many choices do I have? 14. Well, it's 13. N minus 1. Then how many choices do I have?
12.
And then how many?
10.
And so on. So it's going to be n times n minus 1 times n minus 2 times n minus 3 times 1. It follows like a factorial thing. We could get fancy and be like, well, half of them are going to be the reverse order, which are the same, so you can divide it by 2, but we're not going to think about that. So how many possible... No. What is 14 factorial? Ooh, 1, 2, 3, 1, 2, 3, 1, 2, 3. 87 billion, 298,291,200. A lot. Well, let's say there's like 100 cities. 100's not even that big when you think of total number of cities you got to visit. Times 10 to the 157. 157 zeros after a 9. Anyone know how many hydrogen atoms there are in the universe?
A lot less than that. I think 10 to the 80.
It gives us an approximation of 10 to the 80 atoms in the observable universe. We could take every possible ordering of 100 cities assign them to an atom, and we'd run out of atoms. That's crazy. So your algorithm is guaranteed to work if you come back in 50 trillion bagillion years. All right, we'll pick it up Friday.